There is a truck operating right now in the copper mines of Chile that generates its own electricity while it drives, not to save fuel, not to charge a battery, but because without that electricity, the machine physically cannot move. Its rear wheels are not connected to the engine by any shaft, any gearbox, or any driveline component of any kind. They are powered entirely by electric motors, and those motors are fed by a generator spun by a diesel engine. So large it has 20 cylinders and displaces nearly 100 liters. This is not a hybrid vehicle in any sense you have encountered before. This is something else entirely. This is the Liebherr T282C, and the engineering decisions that produced it changed the entire mining industry forever. Most people, if they encountered one on a road, would simply not believe what they were looking at. The scale is wrong. The proportions are wrong. Everything about the visual experience tells your brain that what you are seeing cannot be real. It must be a movie prop or a rendering. It is not. It is a working vehicle, deployed in some of the harshest environments on Earth, performing a job that no smaller machine could do economically every day, around the clock, for years at a time. But before we talk about what makes the T282C extraordinary, we need to talk about the problem it was built to solve, because the problem is more interesting than most people realize, and the solution came from a place that will genuinely surprise you. The open-pit mines operate by a single brutal economic logic. Ore is buried under rock. To reach it, you move the rock. To move the rock profitably, you need trucks, and the economics are governed by one number: cost per ton moved. Everything else is secondary: fuel, tires, maintenance, labor, and capital cost per ton. Every decision traces back to that single metric, and the way you improve it, the way you move more tons for less money, is to make the truck bigger, faster, and more reliable. That sounds simple. It is not. Because making a truck bigger creates problems that compound faster than the benefits accumulate. Bigger payload means more weight on the tires, and tires are already at the engineering limit of what rubber and steel can support. More weight means more stress on the frame, and frames are already pushed to the boundary of what steel alloys can sustain. More power means more heat, and heat is the enemy. And more complexity means more failure modes in remote locations. Liebherr's engineers looked at these constraints and arrived at a conclusion that was, at the time, genuinely radical. The mechanical drivetrain was the limiting factor. It was heavy, complex, and absorbed power through friction. The solution was to eliminate it entirely. And that decision produced the T282C, a truck with no drive shafts or conventional transmission. Just electricity, generated on board, used on board, immediately, continuously, with a precision no mechanical system could match. But that's not even the most incredible part, because the technology Liebherr borrowed didn't come from cars or aerospace. It came from railroads, and the reason it came from railroads will tell you why it works so well in a machine this size. Diesel-electric drive is not a new idea. It has been powering locomotives since the 1930s. The logic is simple and elegant. A diesel engine is most efficient at a relatively narrow range of speeds, but a vehicle needs to move at many different speeds under many different load conditions. Connecting the engine directly to the wheels requires a complex transmission to manage the mismatch. But if the engine drives a generator instead, and the generator powers electric motors at the wheels, the engine can run at its optimal speed continuously, while the electric motors handle all the variation in vehicle speed and load. No transmission, no torque converter, no gear changes, just smooth, immediate, perfectly controllable power delivery from a standstill to maximum speed. In a locomotive, this system works because the wheels are on rails, the loads are predictable, the terrain is flat, but in an ultra-class mining truck, the terrain is anything but flat. The loads are enormous and constantly varying. The environment is hostile, and the demands on the drive system are far more extreme than anything a locomotive encounters in normal service. Liebherr's engineers had to take the diesel-electric concept and redesign it from the ground up for this environment. The generator had to be more powerful than any generator previously installed in a wheeled vehicle. The electric motors at the rear wheels had to deliver massive torque. Starting from 0 RPM loaded with 363 metric tons, climbing a grade that would challenge a mountain goat. The electronics controlling the power flow had to respond in milliseconds, and every component had to survive years of operation in dust, heat, cold, and vibration that would destroy commercial-grade equipment. The result is a system that centers on a MTU Detroit diesel 20V4000 engine producing 3,650 horsepower, 20 cylinders, a displacement approaching 95 liters. This engine drives a generator that feeds the rear wheel motors. The rear wheels each contain an electric motor that converts electrical energy directly into rotational force. There are no drive shafts, no differentials. The power goes from diesel fuel to wheel rotation in a chain that is remarkably direct and efficient compared to the mechanical alternative. When the truck is going downhill, fighting gravity on a steep mine ramp, the electric motors reverse their function. Instead of consuming electricity, they resist the rotation of the wheels and generate electricity. This is dynamic retarding. First, it slows the truck without using the service brakes at all, eliminating the risk of extreme heat and brake fade. The electric motors absorb the kinetic energy and convert it to electricity. The service brakes are held in reserve for genuine emergencies. In the T282C, this energy goes to a bank of resistor grids mounted on the frame, where it is dissipated as heat. The diesel-electric system delivered efficiency improvements that exceeded projections, particularly on mixed haul cycles. Less fuel per ton moved. The system didn't just work, it worked better than anyone had promised. But the fuel savings were only part of the story, and the real reason mine operators chose the T282C was something else entirely. Let's talk about the numbers. Because the T282C's dimensions are in a category that requires new mental frameworks to fully appreciate. The truck stands approximately 7.4 meters tall when loaded. That is taller than a standard two-story residential building. Its width stretches to just over 9.5 meters, wider than 3 standard U.S. interstate traffic lanes placed side by side. Its overall length runs approximately 14.5 meters. To park one in a typical neighborhood, you would need to demolish 3 houses for space. The payload capacity is 363 metric tons in one load. That is equivalent to loading approximately 250 fully equipped Ford F-150 pickup trucks. It hauls them up steep inclines, every trip, all day, in temperatures ranging from extreme desert heat to brutal Canadian winters. The gross vehicle weight, when loaded, reaches approximately 592,000 kilograms. No public road on Earth was built to support this. The T282C exists exclusively inside mine sites, on specially engineered haul roads built specifically to carry it. These roads are maintained continuously by motor graders like the Caterpillar 24 and monitored around the clock to prevent catastrophic failure. Now let's talk about the tires. Each tire stands 4 meters tall and weighs approximately 5,300 kilograms. Each one costs up to $50,000. The rubber sitting underneath this machine at any moment is worth over $250,000. Those tires operate in conditions designed to destroy them. Sharp rock fragments, extreme temperature cycling, and constant heavy loading. Specialized teams monitor pressure and temperature on every tire continuously using sensors integrated into the wheel assemblies. Dedicated tire handler machines are stationed at the mine specifically to change these tires, a process that takes several hours. The T282C's diesel-electric drive system eliminates mechanical connections, which also eliminates destructive drivetrain shock loading. The electric wheel motors deliver torque with perfect smoothness. There are no gear changes and no torque spikes. Traction control electronics modulate motor output independently at each rear wheel, preventing slip before it starts. This result translates into significant cost savings over the machine's lifetime, reducing the need for universal joints and transmissions. In the economic calculus of ownership, the T282C's diesel-electric simplicity is not just an engineering advantage, it is a financial one. The cab and safety systems represent a level of sophistication that would have seemed like science fiction to miners a generation ago. Accessing the cab of a Liebherr T282C begins with a staircase, a real staircase, 3 flights, with handrails and intermediate landings. The climb from ground level takes you past the engine compartment and hydraulic reservoirs the size of compact cars. You pass fuel tanks that run along the frame like cargo containers and cabinets housing the power electronics for the drive system. By the time you reach the cab door, you are standing at an elevation higher than the roof of a standard single-story building. The view from the landing, looking across a mine pit that might stretch 3 kilometers, is genuinely disorienting the first time. Inside the cab, the environment is sealed, pressurized, and climate-controlled. The pressurization prevents the ingress of fine silica dust. This silica dust is toxic to human lungs and destructive to electronics. The cab is a clean room in a dirty environment. This is not a luxury. It is an engineering necessity. The operator's station centers on a suspension seat, an air-cushioned unit. It isolates the occupant from vibration and shock that even the best-maintained haul roads transmit into a machine this heavy. 12-hour shifts are standard. A seat transmitting every road irregularity would produce injuries that no operation could sustain. The suspension seat is occupational health engineering with direct operational implications. The instrument cluster combines analog and digital. LCD screens display machine health, camera feeds, payload weight, and the status of the diesel-electric drive system. A dedicated payload monitoring display shows the operator exactly how much material is loaded in real time as the bed fills. Overloading accelerates tire wear, increases frame stress, and shortens the lifespan of electric motors in ways that are expensive. The camera system covers every critical blind spot. The T282C is so wide that camera assistance is required for ground visibility. Reversing into a loading position is performed on camera feeds, often supplemented by proximity detection sensors. In an environment with light vehicles and personnel, obstacle detection is an operational survival requirement for a 600,000-kilogram machine. Modern deployments are integrated into fleet management systems, GPS platforms that track every vehicle in the mine simultaneously. Data analysis has transformed mine management from an art based on experience into a science based on real-time data. Data revealed that the single largest driver of productivity variation was not the trucks themselves. It was the roads. Mines with better road maintenance achieved higher productivity. The trucks were capable. The roads were the constraint. The T282C's story doesn't end inside the mine. Its impact extends far beyond the pit walls to the scale of global engineering. There are currently Liebherr T282C trucks operating on multiple continents simultaneously. In the copper mines of Chile's Atacama Desert, fleets of T282C trucks cycle continuously, loading and dumping ore. This ore will eventually become the copper wiring in electric vehicle charging infrastructure and the conductors in the power grids the modern world runs on. The global energy transition requires more copper per unit of energy capacity than any previous technology. Wind turbines, solar installations, all are copper-intensive. In Western Australia's Pilbara region, T282C trucks move the iron ore that feeds steel mills producing structural steel for skyscrapers and bridges. Ultra-class haul trucks operating at maximum efficiency are the difference between a viable operation and one that cannot compete on global commodity markets. In Canada's oil sands, T282C trucks operate in conditions that test every system. Winter temperatures drop to -40 degrees Celsius. The material is abrasive and heavy. The haul roads freeze and thaw. Yet the T282C was designed for all of it. A well-operated T282C will move tens of millions of tons of material over its lifetime, creating value measured in billions of dollars. The diesel-electric ultra-class haul truck has become the dominant technology because it works better than anything else. Consistently. reliably. A fully loaded T282C beginning an uphill haul is a sight to behold. The engine note changes as the generator load increases. Nearly 600,000 kilograms of steel and ore begins to climb purposefully. It doesn't struggle, it simply climbs. In the T282C, diesel-electric drive became a wheeled vehicle carrying 363 metric tons in the desert, in the dark, every day, for years. That is engineering at its absolute limit, and that limit keeps moving. Next, we move to a machine that makes the T282C look small. It is the Bagger 293, the largest land vehicle in history.